Imagine a bustling highway, full of cars moving freely. Now picture that same highway, but with speed bumps, narrow lanes, and even construction zones. These obstacles slow down traffic, making it harder for cars to reach their destination. In the world of electricity, there's a similar force at play, an unseen opposition to the flow of current. This fundamental concept is electrical resistance. Electrical resistance is the opposition a material offers to the flow of electric current. Think of it as the friction that electrons encounter as they try to move through a conductor. Every material has some degree of resistance, from highly conductive metals like copper to insulators like rubber. This opposition converts electrical energy into other forms, often heat. Understanding resistance is crucial because it dictates how much current flows through a circuit for a given voltage, and how much energy is lost or transformed in the process. It's a cornerstone of electrical engineering and electronics. The relationship between voltage, current, and resistance is beautifully encapsulated by Ohm's law. This foundational principle states that the current flowing through a conductor between 2 points is directly proportional to the voltage across the 2 points and inversely proportional to the resistance between them. Simply put, voltage equals current times resistance, or V var I R. If you increase the voltage, the current increases, assuming resistance stays constant. Conversely, if you increase the resistance, the current decreases for the same voltage. This law allows us to predict and control electrical behavior in countless applications, from simple circuits to complex power grids. Several key factors determine a material's electrical resistance. These include the material's inherent properties, its physical dimensions, and even its temperature. Understanding these factors helps us choose the right materials for specific electrical applications. Different materials inherently resist current flow to varying degrees. This intrinsic property is called resistivity, denoted by the Greek letter rho. Conductors like copper and silver have very low resistivity, allowing electrons to move easily. Insulators like glass and plastic have extremely high resistivity, effectively blocking current. Semiconductors like silicon fall somewhere in between, and their resistivity can be controlled. The longer a conductor, the more resistance it offers. Imagine a long, narrow pipe. Water flowing through it experiences more friction than in a short pipe. Similarly, electrons traveling a greater distance through a material encounter more obstacles, leading to higher resistance. This is why long transmission lines experience some power loss. The cross-sectional area of a conductor is inversely proportional to its resistance. A thicker wire has less resistance than a thinner wire of the same material and length. Think of a wide highway versus a narrow road. More lanes allow more cars to pass easily. A larger area provides more pathways for electrons, reducing the overall opposition to their flow. For most conductors, resistance increases with temperature. As a material heats up, its atoms vibrate more vigorously, making it harder for electrons to pass through without collisions. This effect is significant in many electrical components and must be accounted for in circuit design, especially in high-power applications. Some materials, like semiconductors, exhibit the opposite behavior, with resistance decreasing as temperature rises. Resistors are components specifically designed to introduce a known amount of resistance into a circuit. They come in various forms, each suited for different applications. Fixed resistors have a constant resistance value that cannot be changed. Common types include carbon composition, metal film, and wire wound resistors. Carbon composition resistors are inexpensive, but have lower precision. Metal film resistors offer higher precision and stability. Wire wound resistors are made by winding a resistive wire around a non-conductive core, suitable for high-power applications. Variable resistors allow their resistance to be adjusted. Potentiometers are three-terminal variable resistors used to control voltage, often found in volume controls or dimmer switches. Rheostats are two-terminal variable resistors used to control current, typically in higher power applications. Adjusting these components changes the effective length of the resistive path. Beyond standard fixed and variable types, there are specialized resistors with unique properties. Thermistors change resistance significantly with temperature, making them useful as temperature sensors. Photoresistors, or light-dependent resistors, LDRs, change resistance based on light intensity, used in light sensors. Varistors change resistance based on voltage, protecting circuits from voltage surges. Resistance isn't just a theoretical concept. It's at the heart of countless devices we use every day. Understanding its applications helps demystify how our world works. One of the most direct applications of resistance is in heating. When current flows through a material with high resistance, electrical energy is converted into heat. This principle is used in toasters, electric kettles, hair dryers, and electric heaters. The resistive wire, often nichrome, gets hot enough to toast bread or boil water. Traditional incandescent light bulbs rely on resistance to produce light. A thin tungsten filament has high resistance. When current passes through it, the filament heats up to extreme temperatures, becoming incandescent and emitting light. This is a classic example of resistance converting electrical energy into both heat and light. Fuses are safety devices that use resistance to protect circuits from overcurrents. A fuse contains a thin wire designed to have a specific resistance. If the current exceeds a safe limit, the wire heats up and melts due to its resistance, breaking the circuit and preventing damage to more expensive components or fire hazards. Variable resistors are essential for controlling electrical parameters. The volume knob on your stereo is a potentiometer, varying the resistance to adjust the signal strength. Light dimmers use variable resistors to control the brightness of lights by limiting the current flowing to the bulb. This precise control is vital in many electronic systems. Many sensors rely on changes in resistance. Thermistors, for instance, are used in thermometers and temperature control systems. Their resistance changes predictably with temperature, allowing electronic circuits to measure and respond to thermal variations. Similarly, LDRs are used in automatic streetlights, detecting ambient light levels by their changing resistance. Even in power transmission, resistance plays a role. While transmission lines are made of highly conductive materials like copper or aluminum, they still possess some resistance due to their immense length. This resistance leads to power loss in the form of heat during transmission, which is why high voltages are used to minimize current and thus reduce these losses. Understanding electrical resistance is not just academic, it's practical. For engineers, it's fundamental to designing efficient and safe circuits, selecting appropriate components, and troubleshooting problems. For hobbyists, it empowers them to build and modify electronic projects with confidence. For technicians, it's key to diagnosing faults and performing repairs. Resistance is the silent gatekeeper of electron flow, shaping how electricity behaves in every circuit, every device, and every system. By grasping this concept, you unlock a deeper understanding of the electrical world around you, enabling innovation, efficiency, and safety in all things electric.